Hello everybody, it is April 16, 2018, time's about 20:53, and this is going to be about the lunar observations I plan on making on April 27th, the night of the 27th and 28th, and I apologize for a lot of these videos lately, but winter's still here where I am, and my cabin still has like 2 feet of snow on it, so the field season is going to start late this year, so I'm trying to occupy my interest with my astronomical hobby as opposed to my actual profession. All right, so as you've seen in the last video, which I'll link below, I showed you why at moonrise or moonset Tycho crater would be tilted relative to your latitude and complementary angles and all that. Well, here is moonrise for the 27th of April 2018. It also gives moonset, but you got to be careful when you go to mooncalc.org and you're getting moonrise and moonset. If you're going to use the length that the moon's going to be up, you have to pick the moonrise for the day before, for the day of actual moonrise, and your moonset has to be the day of the actual moonset. Like me pulling moonset from April 27th isn't going to do me any good because the moon isn't going to set till the 28th for me. All right, so as you can see here on the right, it's just blown up a little bit so you can see it better. Okay, so what I'm going to do is I'm going to make 5 observations. Observation 1 and 5 theoretically are to be made directly at moonrise and moonset, which is not going to happen because I won't be able to physically see the moon. So it's going to be, observation 1 will be a little bit after moonrise. Here's the planned time. And I am going to abbreviate, like observation 1 will be 01. Observation 2 will be 02, etc., etc., etc. Just throughout the video so you know, okay? So here's 1. This is observation 2. You look at the left for the time I plan on taking it. I plan on taking it at 2022. This is all in central daylight savings time, okay? So this is observation 3, which will be at 23:24 on the 27th. Here's observation... Oh, wait, sorry. This is mooncalculator.org's lunar midnight. As you can see, it's a couple minutes ahead of what... My observation 3 is supposed to be at lunar midnight or at my zenith, but mine's a couple of minutes behind what mooncalc.org says lunar midnight will be for me, and that's just a rounding artifact when I was running the equations, which I will show you how I'm going to go through and how I'm predicting where Tycho crater should look from my vantage point throughout the night. So here is observation 4, which will be actually on the 28th at 02:26, plus or minus a couple minutes. I do expect, if there's clouds rolling through or something, I may not be able to get observation 4 exactly at 2:26. I might get it at 2:28 or 2:20 or 2:30 even. So, I mean, there is the weather factor I have to consider. And this is just observation 5. As you can see, I'm going to try to make it right before sunrise. But right before moonset. The moon is not full at this time. I'm doing that on purpose. Because the full moon, Sarah's camera works great. It's a D5300, but the full moon's still kind of bright, and a lot of times the pictures don't turn out, as I've noted before. So I want to do this when the moon isn't quite full, but close to full, so you can still see Tycho crater, and we can still see that sway. Okay, so here is dial-a-moon for all 5 observations. There's just the basic information on 1, 2, 3, 4, and 5 if you're interested. Why am I showing you that? Well, because I need to calculate Tycho's crater's position from my vantage point from observation 1 to observation 5. So essentially all I did was I took a mean average and then just rounded it back up to 5. The math is there below and why I picked 5. The actual average is 4.85, but with the equipment I have and a leveling tripod, I'm not going to ever be that accurate, so a whole number degree is better, or half a degree might be as accurate as I can get, so I just rounded up to the 5. All right, so using 05 By base, I meant not by base. Sorry, I didn't catch that. For each observation, the moon at my latitude of about 41 degrees north should appear to be rotated from my vantage point. That rotation will change throughout the night, and Tycho crater will swing from my right to left at the complementary angle for my latitude for moonrise and moonset, which I explained in the video before. The complementary angle for 41 degrees is 49. 90 minus 41 is 49. And this is about a 24.5 degree change between each planned observation. How did I calculate that? There's the raw math. 49 degrees times 2, because it'll be going from 49 to 49, so you multiply it by 2 equals 98 degrees, and I divide it by 4 to get 24.5 degrees. Well, why not divide it by my number of observations? Well, because the moonrise is an initial point. So what you got to do is you have to divide by the number of spaces in between your observations. And I have 4 spaces in between my 5 observations. That's what you have to do. And I actually set up an equation down here below if you're interested, if you're one of those algebraic people. But it's basically, that equation in black is basically the math I did, and the last part written in white. Okay, so now here are my predictions for all 5 observations. There's 01, there's 02, there's 03, there's 04, and there is 05. So this is what I expect to see, how Tycho's going to look. And Tycho's the red and yellow dot that you see. Well, it looks more red here, but there's a yellow center to it for each of the moon. And I'm measuring the sway from the, you see the crosshairs in the moon here. I'm measuring the sway from the vertical. All right, the other crosshair is just so I can line up my angle. Okay, so that's what I expect to see in my 5 observations overnight. And I actually expect my margin of error, assuming my tripod is level, and assuming I can get every measurement at every minute I plan on getting, my margin of error should be less than 2 degrees. However, if the tripod for some reason is not exactly level, and what I might have to do is, I plan on doing this in the same place I did the lunar eclipse video, that really lengthy one, because it's the only place I can really watch moonrise and moonset for me. But if it gets too cold or whatnot, I may have to come back to where I live, which isn't that far, and that's going to mess with it a little bit. So if I have to move the camera a little bit, or if it isn't perfectly level, or if I can't get the exact time, my margin of error our margin of errors are expected to be about plus or minus that 5 degrees. But I think I can get this pretty good as long as weather is cooperative. So here's all 5 of them raw, and this is just the vantage point throughout the night of me having to look at the moon. Because remember, the moon is also moving through its orbit as well. But I just wanted to show you that because the Earth rotates under us, and that's what causes this sway. We would not get this sway if the Earth wasn't rotating. Tycho crater, even if the Earth was not rotating but the moon was moving in its orbit, Tycho crater would just point a direction in the sky, and it wouldn't move throughout the night. We would just see that. And if I could, during the daytime, if I could see through the Earth, if it were transparent, that sway, I would be able to see that sway coming back around. All right? So it basically sways from right to left during the night, from left to right during the day. Obviously, the moon moves through its orbit and has phases, so it's not exactly at 12-hour intervals every day. And the moon, progressively as it moves from full moon to new moon, is increasingly out longer during the day, which is exactly what you would expect to find if the Earth was orbiting and pointing this, and the Earth was orbiting around the sun, and the moon was orbiting the Earth, and the moon was facing the sun. Because remember, the lit part of the lunar disk is just the daylight side of the moon. That's it. And during a new moon, even though we don't see it readily with our eyes, it is there. The supposed dark side of the moon is actually lit at that point. So there's no true dark side of the moon. It's just during a new moon, the side we observe is in darkness. It's the nighttime side of that moon. That's why we get solar eclipses, when the moon's orbit crosses the ecliptic. So, and we get lunar eclipses only during full moons because of the opposite. The moon crosses the ecliptic in a full moon phase. But anyway, that's it. feel free to comment, ask questions below, this experiment is mine that I have set up and come up with, and it'll be really interesting to see if this is actually what happens as predicted. But anyway, that's it, and I hope you learned something.